Hello everybody, my name is Václav Pritzl. I'm from the Czech Technical University in Prague, and I'd like to show you our results on the autonomous flying into buildings in a firefighting scenario. Our research is mainly motivated by real firefighting scenarios where we believe that the use of UAVs could be really helpful to human firefighters in case of fires in high-rise buildings. In such situations, the UAVs could very quickly reach the upper floors of those buildings. They could not only help with the detection and localization of such fires, but also with actually extinguishing these fires, for example, using fire extinguishing capsules. The second motivation behind our research was our participation in the Mohammed bin Zayed International Robotics Challenge, which took place in Abu Dhabi in 2020, and where one of the challenges was to extinguish an artificial fire located inside a mock-up model of a high-rise building. The actual task explored in this paper is to detect a window which could then be used as an entrance to that building. We assume that all the algorithms need to be able to run completely on board the UAV, and the UAV needs to be able to perform this task completely autonomously. We assume that either no a priori information about the window is available, or a priori information about the window size and window altitude is available. Once we have the detections of the window available, we need to be able to continuously track the position of the window during the entire flight through the window. And we also need to be able to generate and actually execute a safe collision-free trajectory through the window into the building. As for the hardware that we employ for this task, we assume that the UAV carries a 2D LiDAR. In our case, we use the RP LiDAR A3 and a depth camera. In our case, we use the RealSense D435 camera. We also use an upward-facing and a downward-facing laser rangefinder, which are used for providing data about the UAV altitude. For the window detection, we utilize the data from depth camera, which contains the full 3D information about the window. So we process the data in the way that we first downsample it in order to decrease the computational requirements on the CPU. Then we search for contours in the depth image, and then we try to fit quadrilateral shapes to the data in order to try to find shapes in the image corresponding to windows on a wall of a building. The disadvantage of using a depth camera is that its performance is heavily corrupted by smoke, so in a firefighting scenario, this approach is usable only in some cases. Therefore, we also employ the 2D LiDAR for the window detection. Using the 2D LiDAR, we are able to detect the left and right edges of the windows. We do this in the way that we pass the data through a combination of simple line extraction algorithms, which we use to detect candidates on the left and right edges of each window. And we then fuse the detections of these candidates with the depth camera detections or with the a priori information available about the window. Once we have the detections available, we pass these detections to an estimator based on a linear Kalman filter, which estimates the 3D position of the center of the window, the orientation of the window in the horizontal plane, and the actual size of the window, consisting of the width and height of the window. This estimator enables three different modes of operation. The first mode of operation is the use of the depth camera data combined with the 2D LiDAR data with no a priori information available. This approach has the advantage that it doesn't require any a priori information, but the depth camera performance is corrupted by smoke, so it's only usable in some cases. The second mode of estimation is the use of depth camera data combined with 2D LiDAR data combined with a priori information about the window size and window altitude. This mode of estimation enables us to actually initialize the window estimates even when the window is not yet fully visible in the field of view of the camera, which can happen, for example, when the UAV is moving very closely to the building. So it often happens that it sees only a part of the window and not the complete window. This enables us to speed up the detections. And finally, the last mode of estimation uses the 2D LiDAR data combined with a priori information about the window size and altitude, which is capable of working even in a smoke-filled environment under decreased visibility conditions. In order to enable a safe flight through the window and safe flight while inside the building, we have also designed an altitude filtering approach, which provides the UAV software with reliable altitude measurements. The system that we use employs laser rangefinders for measuring the UAV height above the ground. However, these measurements contain large sudden changes when the UAV flies over obstacles or when it flies through a window, or even larger changes when the UAV flies into an upper floor of a building. Therefore, we have developed an altitude filtering algorithm based on a combination of median filters, which filters these changes and provides the UAV software with reliable measurements. Also, when the UAV is inside, we employ data from two laser rangefinders, one of them facing up and measuring the distance from the ceiling, and the other one facing down and measuring the distance from the floor. Once we have the window detections available and the position and parameters of the window are reliably estimated, we need to be able to actually generate a path through the window and execute it. This generation is controlled by a finite state machine, which generates paths through the window based on the actual phase of the fly-through maneuver. These paths are generated as line segments, which are then passed to a reference tracker based on linear model predictive control. This reference tracker generates a feasible reference for the UAV geometric tracking controller, which is then actually employed for tracking the trajectory. Finally, I'd like to show you our experimental results. In the first flight, the windows were detected using a combination of depth camera data combined with 2D LiDAR data with no a priori information available. In this case, the UAV detected a window on the first floor of our mock-up building. It then entered the building through that window, and while inside the building, it detected another window, which it then used to exit the building. In the second flight, the window was detected using a combination of 2D LiDAR data combined with a priori information about the window size and window altitude. Again, the UAV successfully detected the window, entered the building, flew around the inside of the building, and left the building through the same window again. This first flight was performed under good visibility conditions. While the second flight was performed under decreased visibility conditions in an environment filled with artificially generated smoke. Again, the window was detected using a combination of 2D LiDAR data and a priori information about the window size and altitude. This approach works even under decreased visibility conditions in a smoke-filled environment. And again, the UAV successfully entered the building, flew around the inside of the building while keeping track of the window the whole time, and then it left the building through the same window again. This experiment demonstrates the robustness of our approach to different environmental conditions and shows that it can be used even under decreased visibility conditions in smoke. Finally, to sum up, in our work, we have designed a window detection and estimation approach, which is meant for fully autonomous operation in real-world scenarios, even under various environmental conditions. We have also designed an altitude filtering approach, robust to changing ground elevation and obstacles below the UAV, which enables safe flight over obstacles and safe flight into the building. We generate and execute collision-free trajectories through each window, and we have evaluated our approach both under normal and decreased visibility conditions. We'd like to acknowledge the projects that have funded this work. And if you have any questions, please don't hesitate to contact me. You can also have a look at the video attachment to this paper, and you can also have a look at the open source system that we have used for developing this work and that has enabled us to actually evaluate this work in the real world. Thank you for your attention.